Okay, what we're going to look at this time is the SN2 substitution of a general substrate, and I'm going to use a secondary one since they tend to give students the most trouble. And I'm also going to make it chiral so we can see what happens to a chiral carbon during the course of one of these types of reactions. I think that would be very useful for our purposes. So I'm going to use bromide as our leaving group in this particular reaction. And I've tried deliberately to have next door to it a tertiary carbon because this is one of the major areas of concern for students is, should I form a carbocation or shouldn't I? And if I do form a carbocation, do I need to deal with a shift? How do I know? What do I do? Please help. So first off, we've got a secondary substrate. And what I'm going to put on top of the arrow is a good nucleophile. And I hope you remember what makes something a good nucleophile. We're going to talk about this, but I'm going to use CH3S minus. And now it's got to have a cation. I don't care what the cation is, but it's got to have a cation to balance charges here. Now, if you remember, good nucleophiles that we've talked about from class meet a couple of different requirements. First of all, they have to be a nucleophile, which means they need to be an electron pair donor. And this sulfur does have 3 lone pairs of electrons around it. After we know that it has electron pairs to donate, so it meets the requirement for a nucleophile, we want to know how good of a nucleophile it is. Better nucleophiles have a negative charge. Not all nucleophiles have a negative charge. Things like water, alcohols, and amines can be nucleophiles, but they're not the best ones because they're neutral. Better ones have a negative charge. So if you're trying to choose which one should be a nucleophile, choose one that has a negative charge if it's an option. Next, you want to look at the size of the atom. The larger the atom is, the better the nucleophile it will be, and that has to do with the polarizability. It tends to be a weaker base, and that tends to increase its nucleophilicity. In addition, we would like that negative charge to be localized. You don't want to be seeing a delocalized negative charge. That would be an issue. So those are the things I'm looking at. It needs to be, again, it has to have lone pair electrons. It needs to have a negative charge. It's better if it's a localized negative charge. And it's really helpful if that negative charge is on a large atom. All of those things in conjunction mean that we're dealing with weak bases, so they're not likely to be picking up on a proton and doing an elimination reaction. You do elimination reactions with strong bases. These are weak bases. Also, you need to be looking for the best leaving group on your substrate. In this case, I know it's bromide, but there are 3 things you should be looking for with the leaving group. Number 1, it's got to be a weaker base than the nucleophile that is coming in. So you've got to know if that's true or not. The best leaving groups, number 1, tend to have a delocalized negative charge. You could show that happening through resonance. So those things tend to be things like the tosylate or those sulfonates that come from the sulfate esters. Those are really great leaving groups. If you can't have a delocalized negative charge, it would also be very useful if you're kicking out a neutral molecule like water or an alcohol or an amine. If you've noticed, we never kick out hydroxide on an alcohol. We protonate it and then we kick out water. And that's because we're throwing out a neutral molecule. That's much better. If you can't have a delocalized negative charge or a neutral molecule, the next best thing is to be kicking out a negative charge on a large atom like these halides, because they are the corresponding conjugate bases of really strong acids. So they're really weak bases, and those tend to be good leaving groups. Now, to make sure this goes SN2 in this particular case and not SN1, because it is secondary, what you really need to be looking for is the solvent under the arrow. Now, if the solvent is a polar protic solvent, it tends to go SN1. If the solvent is a polar aprotic solvent, it tends to go more SN2. Now, the difference between those 2 solvent types is the ability to form hydrogen bonds. Polar protic solvents are hydrogen bond capable, meaning you will have an OH or an NH bond present in the solvent molecule. So things like water, alcohols, and amines would force a substrate like this to go through an SN1 mechanism. If you want to do an SN2 mechanism like we want, you want to use something like DMSO, which is what I'm going to use here, DMF, acetonitrile, acetone, something along those lines. You need a solvent that is polar but is not capable of hydrogen bonding. It needs to be polar enough to dissolve ions like we have on top of the arrow, but not polar enough to make them happy. We don't want to put a solvation shell around them. Okay? So these are the conditions we're looking for. So what's going to happen with an SN2 reaction is you can't form a carbocation. So this is an all-in-one concerted reaction. And I'm going to redraw that substrate here for us so we can see it again. What you're going to have happen is a backside attack of your nucleophile on the substrate. And it always needs to occur from the backside. This is so that you have enough room in the transition state for 5 groups to get around there. I'm going to show you that. So I wanted to do this with the chiral carbon. So if the sulfur is making a bond to carbon, carbon can't have 4 bonds. You've got to break the most polarized of these sigma bonds, and that would be the carbon-bromine bond. And bromine, being a little bit more electronegative, gets those electrons in this bond. So that's actually the mechanism for this. This is the slow step for the reaction. It involves the nucleophile and the substrate. That's why it gets a 2 when we say it's substitution nucleophilic 2 bimolecular, because there's 2 chemical species coming together in the transition state. Now on the next slide I'm going to draw the transition state. This is not the mechanism. Okay? It's the transition state. I want to draw it though so that you can see how we get these 5 groups around this carbon at that time. So I'm going to try and redraw what we've got going on here with the appropriate stereochemistry. I'm changing the orientation of things just a little bit. Oops, that's a 2. Okay. The group that is being broken off is the bromide. So in the transition state, it is developing some negative character. And the group that is coming in from the opposite side is this incoming nucleophile. And so it is losing its negative charge. There literally are 5 groups around this carbon in the transition state, as the carbon-bromine bond is being broken and the carbon-sulfur bond is being made. But at all times there are literally only 4 bonds to this carbon, because these are partial bonds. Now if you've got 5 groups around a central atom, I hope you remember from general chemistry that the optimal arrangement is trigonal bipyramidal. That's what this looks like, is trigonal bipyramidal. And that's why you have to have this backside attack. It has the best electron arrangement around the central atom, so that when this reaction is complete, you have inverted the stereocenter on this molecule. So you always are going to have this occur with inversion of configuration at the chiral carbon. Okay, and that's one of the ways we know that it has gone by an SN2 substitution. The product has the opposite stereochemistry of the reagent.